this afternoon's session with our next speaker, who's Kaisa Matoma, who's going to give the final lecture of her course with Maksym on correlations of multiplicative functions.
Okay, thanks. So, unlike Maksym, I'm not starting with primes today, but if I have time, I will end with the primes. But let's see. I will just get into real Wheeler function. So I will first write again the main theorem for the real Wheeler function, which Maksym mentioned in the first talk, and then I will go on talking about how we actually prove it. So this is the same, except that I'm changing the auto I'm writing in full. So we have that as soon as h tends to infinity with x, we have cancellation in the sums of the real Wheeler function in short intervals. So if we look at the sum of the real Wheeler function over a short segment of length h, which we just request to go into infinity with x, we have that there is some cancellation going on, which means that this sum is literal of h, literal of the length, for almost all x. Okay, so in the previous lecture, Maksym showed how to prove this in case h equals to x to epsilon. And now my task is to show how to get from this h to x to epsilon range to shorter and shorter intervals, and eventually to any intervals which have length tending to infinity with h. And the first step is the same as in Maksym's two previous lectures, which is the Parseval step. So I'm just recalling that by Parseval, if we look at the mean or the second moment of what we want to study, so what we would like to have is that this is literal of 1, because then this is literal of h for almost all x. And by Parseval, we know that this thing we want to bound by literal of 1 is at most 1 over x squared times the integral from, say, log x to 100 to x over h of the corresponding Dirichlet polynomial. Okay, and here we are starting not from 0 but from log x to 100, just to make our life later easier. We could just start from the 0 and say that from 0 to log x to 100 there is a lot of cancellation going on here, and we can discard those terms. But in some cases where you look at more general multiplicative functions having main terms, it's actually important that at this step you already have discarded of small t values. And so, as I said, we want this to be literal of 1. And as Maksym discussed, the smaller the h, the longer the integration. So the task of showing that this is literal of 1 becomes more and more difficult when we decrease h, because the length of the integration becomes longer and longer. And eventually we just want that this is x over something tending to infinity. And so we want that this is literal of 1, because that means that this thing here is literal of 1 for most x. And what we get from what Maksym called Montgomery-Vaughan theorem, and what I like to call mean value theorem, but in any case we can write MVT. So the Montgomery-Vaughan or mean value theorem for Dirichlet polynomials gives that this thing here is 1 over x squared times the length of integration plus the length of the polynomial times the 2 norm of the coefficients, which is also x, and so this is big O of 1. So what we need to do is to change this big O of 1 here into a little O of 1 here. So we need to save something, but not much. Okay, so this is sort of same things that are happening on previous days. And actually we are starting the proof in the same way as in case of h equals to x to epsilon. We are choosing some parameters and then we are trying to take out, decompose the polynomial into a product of 2 polynomials in convenient ranges and things like that. So I'm doing sort of similar things as Maksym, but at the end things will evolve into a sort of continue in a different direction or keep on going on and on. But let's start with just recalling how to decompose such polynomial into a product of 2 polynomials. And I start with choosing my parameters. So a difference compared to previous days is that I have pj and qj rather than just p and q, but it's just for greater convenience that I will have several parameters like this. And what I want to do is I want to take out prime factors between pj and qj from my n by force, and I want to guarantee that such prime factors exist. And for that reason, I assume that my pj and qj are such that the sum of the primes between pj and qj, 1 over p, tends to infinity. So this condition here guarantees that almost all integers have a prime factor between pj and qj. And then we use the identity. It's sort of a variant of an identity which is due to Ramaré, and the identity says that if we look at the real function at n, we can decompose it into a product of 2 real functions. So we can write this as a sum where we sum over all products p times m equals to n, where our p is between pj and qj. And we take lambda p times lambda m. Lambda is completely multiplicative, so that since p times m is n, this is actually lambda of n. And we divide by the number of primes that divide m, and which are from this interval between pj and qj. Plus 1. Okay, so this is just to normalize, as m might have several prime factors between pj and qj, so that this sum might have several terms. And now I have been taking out the prime factor from the interval from pj to qj, but such prime factor is not guaranteed to exist, so I have to add another error term corresponding to those integers that don't have a prime factor from that interval. Well, so this is just an identity, but which will allow us to decompose our Dirichlet polynomial into a product of 2 polynomials. And actually I will record this decomposition now. So we can write this Dirichlet polynomial we are interested in as a sum of products of 2 Dirichlet polynomials. So as previously we have to decompose our p's into dyadic ranges. So actually, to be honest, we would have to decompose them into shorter than dyadic ranges, but I want to put them into dyadic ranges for this talk to make notation simpler. So I will write this as a sum of k between log qj and log pj as pk t q kt plus 2 arrows. Okay. And here the important things are these pk's and qk's. So the pk corresponds to the Dirichlet polynomial over primes. And so it's the guy here, and then the q is the corresponding thing with the m. So it's sum of m between 2x e to minus k and x e to minus k minus 1 of lambda m to it over then this number of prime factors. Okay, and these ej and dj are just errors, similarly to Maksym's talk, and we don't care about them today. So. No, I don't sum over j. I do this decomposition for several j's. So I will explain it in a bit. But at the moment, you can just ignore all the j's and think.
You should have j's there in the pk too?
Here. Yes, thanks. So I shouldn't ignore them. Just you should ignore them. So these things here are just arrows, and they are small. And as I said, I'm cheating a bit because I'm having these pk's to go on the e-adic intervals, and this means that this error d is actually too large, but it doesn't make any difference to make them into a bit shorter intervals, except that everything gets more messy, but in that case the error would be fine. But anyways, I will forget about this error, so it doesn't matter that this error is too big in this case.
Excuse me.
Yes?
Why do you add +1 in the denominator here?
Because I have to count also this prime that I'm having at the moment here, so this p here. And then in order to count the number of prime factors n has on this interval, I have to +1 to the number of prime factors m has in this interval.
Oh, it's m, not n.
Yes,
Okay,
so
m.
this is m to
Okay,
make
yeah.
these sort of independent of each other so that they don't depend on. Yeah, thanks. It's a good point. Okay, so by this identity here, I can decompose this polynomial into a product of two things, where I have just made a e-adic decomposition of these primes here, taking each term, taking p to be from the interval from e to k plus 1. So that's why we have this sum here, just to control the size of the two variables. But essentially, this is just decomposing this polynomial into a product of two things. Okay. And next, I want to plug this formula for the lambda n plus it into my Parseval thing there. So for any subset of the integration range, I want to split my integration range into several pieces, and that's why I'm talking about subsets of it. And I'm just taking my j to be anything. Just don't care about it at the moment. Then I write I of t for the integration I have there, but just over the set t. So I want to plug into this place here the formula I have here. And I do it ignoring the error terms. And if I plug this thing here, I get that this an outer summation over k, and I can dispose of it by Cauchy-Schwarz and just multiplying by the number of elements I have here. So this becomes at most log qj over pj squared.
You still want an x squared in the denominator?
Oh yes, here, thanks. Times 1 over x squared times integration over t, and then p k j t q k j t squared dt plus e to the power of 1 for some kj. So essentially what I'm doing here, I'm plugging this thing in, and I'm selecting the k which gives the maximal contribution to the integral, so that I don't have to have a sum over all k's. I can do it in a correct way if I first Cauchy-Schwarz and then change the order of summation and integration and then take the maximum. But anyway, you can just pretend that you take the maximal thing here, the k which gives you the maximal contribution, and then just multiply by the number of different k's, which is log q over p. And so I get this thing here where I multiply by the number of possible k squared, and then I just pick my favorite, not my favorite, I pick the most difficult k, which gives the largest contribution for this integral. And this inequality here holds for all j. I can take any j, and I can take any capital T I want, and it's always true. But these j's will depend on the t, and they will depend, k j's will depend on j, and they actually depend on t as well. So perhaps I should write it here. No. Don't worry about it at the moment. Okay, and now I would like to get a bound of integral of 1 for this integral here, essentially. And I could try to do the same thing as Maksym did previously, and I actually will be trying to do it. I try to give an L infinity bound for p, and then L2 bound for q. But now the problem is that this p is very short polynomial, possibly, so that we don't have an L infinity bound or something like this. But anyway, what I will do is I will split the integration range in several pieces, and in the first piece I will just assume that we have a good L infinity bound for this polynomial p. So I will, at the end I have to handle the whole integration range here, but I will split it into pieces and I will handle them one by one. So I will first handle a sort of easy case, those t's here for which I have good cancellation in my polynomial pk. So I take only those t's in my relevant range. For which I have good cancellation in p k1 of t. So by now and at the moment, just pretend that j equals 1 everywhere. And this polynomial pk1, it has length e to k1, and I wanted to have some cancellation going on, and I will actually request that it has, or look at the set where it has some power cancellation. So I look at the set of those t's that this polynomial pk1 has some power cancellation. Where alpha 1 is something to be chosen between 0 and half. And then I look at this integral over the set D1. So at the moment, I don't hope to handle the whole integral, but I hope that I can at least handle the integral over this small set of t's, and then perhaps I can dispose, or then after that I can assume that I don't have such t's left, and perhaps that will help me. Anyway, I will try to do look what happens for the integral in the set D1. And actually I want to make another notation here. I want to call this guy here, I want to call it the integral of t with j. Okay. So what I want to do is I want to bound this thing here. Okay, so I will look at the integral of this integral here with this set t chosen to be this set t1 and j chosen to be 1. So it's 1 over x squared times, then for the p polynomial I can use this assumption that I'm on set t1, which means that I have good cancellation in this polynomial pk1. Okay, so I'm just using this bound here, and then I'm left with the average of the q polynomial. Okay, and I want to use the Montgomery-Vaughan or the mean value theorem for the q polynomial. So I'm getting for this one the bound 1 over x squared times e to 2k I 1 minus alpha 1 times, then for this integral here I can replace this by a longer integration range from log x to 100 up to x over 8. X over 8, length of the integration times the length of the polynomial times the me L2 norm of the coefficients, which is x over k1. Okay, and if I calculate everything here, I get e to k1 times 1 minus 2 alpha 1 over 8 from the first term, and I get e to minus 2 k1 alpha 1 from the second term. And this is reducible of 1, there is the minus sign. But for the first one, in order to have that this is reducible of 1, I would essentially need that this e to k1 is smaller than 8. And this k1, a to k1 is between p1 and q1, so I need that my q1 is smaller than 8. Okay, so far everything is happening in a similar way as for intervals of length x to epsilon, except that I'm only handling this set of t1. So the problem really is here that I need to have that this length of the polynomial of the p polynomial is at most 8, but if 8 is very small, I can't guarantee any cancellation going on in my p polynomial. So that's sort of the reason why this doesn't immediately work for polynomials of shorter length than x to epsilon. If I looked at 8 to x to epsilon or slightly smaller, then I can just have some cancellation going on in the p polynomial always. But if my h is very small, then my p polynomial will have a very short length, and there is no guarantee that there is cancellation going on in the p polynomial. So I might have that this set of T1 is empty. I can't help it. In particular, if h is very small, perhaps one expects that it's almost empty or something. So it's, or at least it doesn't contain everything. So in the case h equals to x to epsilon, we can make something like this, not this much cancellation, but we didn't need so much cancellation. So we can make this to be everything, and everything works out. But now we would like to go into smaller h's, and then the question is, what can we do? So the problem, then h small, so is p1, q1 smaller than h, t1 not everything. So there is no way to guarantee that T1 contains actually anything. But now the good thing about this is that at least we have shown that this integral over T1 is small because we choose our parameters in this way. And then later on, we can assume that they are not in this set T1, and that will help us. So we will continue in the same way and hope to somehow use later on the fact that we don't have to care about those t's where pk1 is small. So on the other hand, on the other words, we can assume that pk1 is pretty large from now on. So we take p1 smaller than q1, smaller than h, and everything works for t1. And then we want to pick more of these pj's. I didn't write the j just to make things messier, but we will actually need them. So we will choose also qj larger than pj, larger than qj minus 1, larger than pj minus 1, etc., etc. And we will again request that almost all integrals will have a prime factor between qj and pj. Okay, and now we start playing this game for a second round or for the jth round. We will define more sets T1, and eventually we will cover all of our interval from log x to 100 to x over h by some set that we can handle. So what we do is we define Tj to be the set of those t's such that we have cancellation in pkj. And we are not in any of the previous sets. Okay, so for instance, the set T2 is the set of all those t's where we have cancellation in pk2, and we don't have cancellation in pk1. Yes?
How do you choose alpha j if everything between 0 and 1/2?
So I will choose it very in the end.
Okay.
So at the moment, they are just something between 0 and half, but I have to choose them so that everything works. But it's not obvious at the moment how to choose them, so I just say that there are some parameters. So we define this for j, different j's, bunch of different j's, and so that eventually we are getting larger and larger parameters pj and qj, and eventually we will want that our pj, capital J, and qj, capital J are pretty large. Say they are from log x to say 4/5 and (9/10). So the reason for such a choice is that I want to choose these parameters from such a range that I will have some pointwise cancellation going on polynomials over primes of this size. So that's kind of, I want to go little by little toward larger and larger, or longer and longer polynomials, and eventually reach polynomials where I have pointwise saving. And finally, this set still doesn't contain everything, so I define the set U to be the rest. So it's the interval from log x to 100, x/8, and we take away all those. So it's the rest. It's the set of those t's. There we don't have cancellation for any of those p's. And now let's go back to the very first thing we wanted to bound, the integral up there over everything. So as I said, we want to split this integration range into several parts. And the parts you can see now here, they are these tj's and u. They make a partition of my integration range just by definition of u, because u contains everything which is not contained already. So this integral here is surely sum of the corresponding integrals. So this was defined to be the integral over tj, this I of tj. And I can approximate these things or give them upper bound using this formula here. And for looking at tj, I use the formula with j. So these are at most sum of j from j, capital J, log q j squared times this I t j j plus log say q j squared times I of u and j. Okay. So what I did here was that I used for these integrals here the bound I got from the Ramaire type identity here. I just estimated this log q over p by log q and then put into this integral I. Okay, and now our task is to solve that this thing here is literal of 1. So we have some literal of 1 left, and we want that this thing here is literal of 1. And we have actually already taken care of the case where j equals to 1. We saw that this integral over t1 with j equals to 1 is literal of 1. So we don't have to, we still have to multiply by log q1 squared, but we have enough cancellation that that doesn't matter. So j1 is okay. And then we have to move on into larger j's. And we can try to do the same thing as before. I mean, I'm repeating myself, but we can just look at this I of tj, which I defined here. It's a product of two things, and we know that there's cancellation going on in this p polynomial by the definition of our set t, so that we have that this E of j is at most 1 over x squared times then by the definition of tj, we have cancellation in the polynomial p2, pkj, which is involved in this definition of say. So here we can put here the cancellation we are assuming in pkj. So this becomes e to 2k j times 1 minus alpha j. Okay, and then we are left with the q polynomial here. Okay, so we haven't done anything differently. And now what we have been doing previously is to use the mean value theorem or Montgomery-Vaughan for this polynomial here, and we could try to do it here. So if we use MVT, then we get 1 over x squared times e to 2k j times 1 minus alpha j times the length of the integration x over h plus the length of the polynomial x over e to kj times x over e to kj. And if we do the calculation here, we get again the same answer as before. We get e to kj times 1 minus 2 alpha j over h plus e to minus 2 alpha j kj. And as before, in order to win, we would need that this e to kj is at most h. But we wanted this is between pj and qj. But now the problem is that we wanted these pj's and qj's to increase and increase until we reach something where we can show cancellation. And so we can't just keep them below h forever. So this doesn't work. Yeah. The reason why it doesn't work is really that this x over h term starts to dominate here. If this would dominate, then we would only get the second term, which is fine. So the problem is that this polynomial q is too short. This is the length of the polynomial. It's too short. It's shorter than the length of the integration. If it was other way around, everything would work nicely. But the problem is that the polynomial q is too short. And what we want to do next is we want to somehow increase the length of the polynomial q. So we are playing some tricks so that we can increase the length of the polynomial. Okay. So what we do is we use this information that we have. We are assuming that if we're looking at the tj, we are assuming that they are not in the tj minus 1, which means that we know that there exists a polynomial which is pretty large on this set tj. So if we take any t in the set tj, then we know by the definition of tj that it doesn't contain any points from the tj minus 1. And this means that if we look at the polynomial pk j minus 1 at the point t, we know that it's pretty large. We are assuming that they are not in the set tj minus 1 where there is cancellation going on. So there is no cancellation, not so much cancellation going on, so this is pretty large. And being pretty large means by the definition that we have this about like this. So this follows just by the fact that we are in tj, which means we are not in tj minus 1, and the definition of tj minus 1 says that this guy here should be smaller than this, so that if we are not there, then it's larger than this, and then just moving things to the other side, it means that this guy here is at least 1. And here we have then a Dirichlet polynomial times something that we know to be larger than 1. And so we could just take this product here and just this mean value here, and we can increase it by multiplying by this thing which is larger than 1. And then we are having a product of two Dirichlet polynomials here, this q and this p, and it's getting longer. But it doesn't help yet much. But note that if we have something which is larger than 1, if we raise it to any power, say 2a, it's still larger than 1. So now we find this by taking a of appropriate size. We find this pretty long Dirichlet polynomial, which we can sort of add here by the cost or penalty of having to add this e to something as well. And that's exactly what we are going to do next. So this holds for any a. So we are using this trivial sort of inequality that 1 is smaller than this guy here to increase the integral there. So we can write this I of t, j, and j on the right-hand board. We have 1 over x squared as before, and we have this e to 2k j 1 minus alpha j. But then what we do next is that we add this sort of factor there, which gives us e to minus 2a k j minus 1, 1 minus alpha j minus 1 from this term. And then this has to go inside the integral because it depends on t. Anyway, we get this integration over dj of q k j, t as before, but we add this. Okay, so compared to the line here, or the thing here, before we tried to use the mean value theorem, so forget about this, it didn't work. So we go back here, and we just estimate this thing by adding or multiplying it by something larger than 1. So our outcome is certainly larger than the previous thing. And so that will cost us this thing here. But on the other hand, it is giving us a longer Dirichlet polynomial here. So now the length of the Dirichlet polynomial has increased because we have multiplied it by another Dirichlet polynomial. And why this sort of thing has a chance of working is that actually, in the truth, we expect this p to have square root cancellation almost always, and this thing here is less than square root cancellation. So we sort of hope that by the mean value theorem, we saw that it actually has square root cancellation, and this term here gives a smaller contribution than adding the average here. Because, and that's what actually will happen. And what we want to do is we want to choose our power a such that this has an appropriate length so that the mean value theorem works well for it. So we choose this a to be kj over kj minus 1. So remember, this has length e to kj minus 1, so that it to the power a has length e to kj, and this has the length x over e to kj. So this makes this q kj t times p k j minus 1 t to a, which is what square of which we are interested in, have length of size x. And then it has length about x. When we apply the mean value theorem, we will get the length of the integration plus the length of the polynomial. And the length of the polynomial is now x, so that this time the length of the polynomial will dominate, which makes us happy.
Sorry, so you made this whole trick was to expand the length of the Dirichlet polynomial. What was the cost? What do you pay for that?
So I pay this factor here. Yes, but on the other hand, having the Dirichlet polynomial here is making it larger. sort of. I mean, I'm multiplying by something which is larger than 1. But because of the normalization to the 0 line, it's not obvious what is having negative effect and what's having positive effect. But this is sort of the trivial bound, this guy here, and for the Dirichlet polynomial, and this plus 2a kj minus 1 alpha j minus 1 is the cost of doing this thing. So it's this thing which has 2 negative signs is the cost. Sure. Yeah, thanks. Okay, so now we choose this way so that we have this polynomial length x, and this is good for the mean value theorem. And let's go into the board. Okay, so I will give you an exercise as well because I didn't think we had any in this course yet. So this is the first one, but it's the last lecture, so you can't hand it in. But anyway, as an exercise, you can show that the mean value theorem actually works pretty well for this polynomial. So the mean value theorem for this polynomial, it doesn't give exactly the length of the integration plus the length of the polynomial times the length of the polynomial as previously, because there is the mean of the coefficients. And this, having this large power here gives you the mean of the coefficients won't be 1, it will be a bit larger than what you can quite easily show is that this is at most a plus 1 factorial squared times e to a plus k j minus 1 times x squared. Just don't care about this thing, it will be small here. So essentially it's x squared, the mean value of this polynomial, the mean square. And if you don't want to do the exercise, it's a lemma in our paper, so you can just check it from there. Okay, so we will plug this mean value bound into here. And just to make things simpler, let's forget about the fact that this fraction here might not be an integral. Just pretend that it's an integral. So let's pretend that a equals to this thing here, so that we don't have to care about having some ones somewhere. And then doing this thing here gives that this ij, which we had the previous bound is here. So we want to continue from there using the mean value theorem bound, which gives us that this is at most. So this x squared cancels with this x squared here, and this will add some noise to our equation. Essentially of size a plus 1 factorial is about e to a log a, and we have some stuff like that. So this thing here, or you can also include everything here, becomes e to 2a log a plus k j minus 1. So this is the thing coming from the mean value theorem. And then you have this previous thing here. So if we choose a to be the kj over kj minus 1, the first terms here cancel each other. So that's why it's not really contributing this one thing. This kj over kj minus here guarantees that these first things cancel here, and we have this alpha difference of alphas left. Okay, and I can just rearrange these things a little bit and remember the definition of a, which was that it's kj over kj minus 1, which means that this thing here becomes something like kj minus 1 from here, and then this is kj over kj minus 1. So this becomes plus kj times, then we have minus 2 alpha j minus alpha j minus 1, so it comes from here. And then we have this 2a log a left, which contributes something like 2 log kj over kj minus 1. Okay, and now it's quite a mess. But choosing everything very carefully will make this thing here to be negative enough so that it compensates for this positive thing and for this positive thing here and makes this little o of 1, or actually it can be made to be little o of, say, 1 over j squared log qj squared. So remember we had this log q squared coming from the fact that we made the e-adic decomposition, so we have to win for it. So eventually, if you choose your parameters very carefully, you get bound like this. And I can write some choices of parameters. Okay, I can't raise this board up. So if choose, so we can take, for instance, there are a lot of choices that work, but one is that we take each alpha j to be, say, 1 over 5 minus 1 over 40j, which means that this difference of 2 alphas is about 1 over j squared times something. And we can take q1 to be 8 and p1 to be log q1 to 800, say. But remember, we wanted that q1 is smaller than 8, or at most 8, and it happens now. And then we just have to define our pj and qj. And so we take pj to be something pretty ugly, but I just want to show you that there are choices that work, and you can try it at home to work out that they actually work. But you just would have to plug in these things there to so that it works. P1. So this is the pj, and for qj, one can take, for instance, for y times log q1 to j. Okay, so with these choices here, we get that this I of tj is of this size, and we can plug it in here, which makes this thing here to be little o of 1 over j squared, and then with sum over j it becomes little o of 1. So when we bring everything back here, this thing becomes little o of 1, except that we still need to handle this exceptional set there. We don't have cancellation in any of these p polynomials. But this thing handles that this guy here is little o of 1, this first thing. So what we have shown is that this, it's very small. Okay, this is very small little o of 1, but it's up there. And I should say that we have here, for these choices of pj and qj, these are actually iterated exponentials sort of thing. Well, it's not obvious from the definition, but anyway, it's sort of, the first ones are like 8 and log 8, and then we go up to exp of 8 something and exp. And if we would do it other way around, we would start with x to epsilon about, and we would go down to log x, log x, log x. So this is analytic number theory, but I'm hiding it here.
Everything you've already said works for lambda n equals 1, right? So far. You haven't used any.
Yes, I haven't used anything about lambda yet. So it's the u part for which it's the last part where I have to actually use some property of the lambda function. Yes, you're right.
So for free, you can just move your. You can move qi, qj to the size of q, like log x to a power, right?
Yes, sort of. Yes, yes, sort of. like this. Okay. And also the theorem does work for the lambda n equal to 1, but you just have the main term in that case. So yeah. Okay, so in the last few minutes I will try to say a bit about how to handle the remaining thing, this integral over the set U. So the set U is the set of those t's where you don't have cancellation in any of these p polynomials, and I just use the fact that we don't have cancellation in the pk, capital J, which is the longest polynomial and most useful. So the first thing to note is that this U is contained in the set of those t's. Such that this pkj doesn't have the voted cancellation, and so it's of size j 1 minus alpha j. And now I chose my alpha j's to be a bit smaller than 1 over 5 here. So this alpha j is a bit smaller than 1 over 5, which means that we can replace this thing here by 4 over 5. Okay, so I have this polynomial over the primes, which has length e to kj, and I know that it doesn't have cancellation of size, the polynomial to 1 over 5 or something like this. And it's possible to show that it's quite rare that this sort of things would happen. I mean that this set of t is pretty sparse, and it's the second exercise, which also I remind the paper. So to show that this set U has size x over h to the 2 over 5 plus epsilon c. Okay, so it has the, I mean, it could be of size x to h, but it's only of size x to h to 2 over 5, so it's pretty small. So this is a pretty rare event, and how to prove this exercise is to use the mean value theorem to a high power of this polynomial, and it's in the paper, so it's. And so we know at least that this set U is very sparse, but we still have to handle it. And still everything works for any polynomial supported on primes. We don't use that it's the real Wheeler function. And then one could hope that this Montgomery-Vaughan thing could be improved a bit in case we are just integrating over a very sparse set of the points, and that's what we are going to use. And this is the lemma due to Haras and Montgomery. Which says that if we have any complex numbers and we have a set T which is well spaced, meaning that dy minus dj is at least 1 for I not equal to j. Then if we look at the mean square of a Dirichlet polynomial over such a set, oh, it's okay. I think I didn't use a capital T for anything. Really, it's dj, so I'm not using the same notation. Good. So if we look at the Dirichlet polynomial, and instead of a continuous average, this thing has a discrete average, but it doesn't make much difference, really. Then this mean square is at most the length of the polynomial, similar to Montgomery-Vaughan, but now we have the size of the set we are looking at times a square root of t times some redundant log t times the mean square of the coefficients. And the point here is now that previously, when we applied the mean value theorem, we had a capital T here. And we were in trouble if this capital T was larger than this n. But now we have just square root of t times the size of t, and in our case the size of t will be t to 2 over 5. So there is some polynomial saving compared to t, which makes that this term will actually dominate when we apply this sort of theorem. So this was t in the mean value theorem. And so now thanks to this thing here, writing one last thing. If we look at this remaining thing, this integral over u, j, it's at most 1 over x squared times, remember that it's the integral mean square of p times q, and we can take the p out, so it's supremum of t between log x to 100 and x over 8 of p k j t squared times the integral over the set u of this q k j t squared. Okay, and now for this thing, instead of using the Montgomery-Vaughan, we can use Halas-Montgomery, which saves us in this place. In our case, when this size of the set is at most t to 2 over 5, this n term will dominate and it will be giving good contribution for us. And for this one, we can use pointwise saving because we were taking our pj's and qj's grow little by little, so that eventually we were in the range where this capital P capital J and Q capital J, they're of size x of log x to something large enough that the prime number theorem applies. So for this thing here, we get the bound that this is at most 1 over x squared times log x to minus 200. So that's the saving we get from this supremum by the zero-free region for the zeta function. And then for this thing here, we get that it's at most the length of the, okay, so e to 2kj, which is the length of the p polynomial, times x over e to kj plus t to x over h to 9 over 10 times x to e over kj, and now this guy dominates here, so we get log x to minus 200, which is liter of 1. So this is the place where we use that we actually have real bigger function. We have cancellation for this polynomial here. And for general multiplicative functions, you have to be a bit more careful because you don't necessarily have such a supremum bound here. But then you do have a supremum bound for this q polynomial due to Halas' theorem for multiplicative functions, and then you can prove and use a different sort of Halas-Montgomery for the polynomials over primes and work out that things actually work for general multiplicative function as well. But I don't have time to go into that. Okay, so I will stop here. Thanks.
Okay, thanks a lot, Kaisa. Are there any questions?
So, I might have misunderstood, but my sense is that the main idea is this identity you wrote down in the beginning for lambda of n, and the corresponding identity for lambda of n times n to the it. And I guess, I don't know what you're thinking, but I guess you must have realized that doing so would help you make all the analysis work. I guess, can I ask why you were able to anticipate that this would all work out?
So of course we didn't know that it will all work out, but it was a gradual progress that we got down to any h. So we started with x to epsilon, actually with the first result where we didn't do this sort of iterative argument, and eventually it we were going down and found this iterative argument which turned out to work. But I think the two main ideas are really the identity, as you said, and also this thing of pushing in the large Dirichlet polynomial and doing this iteration.
Yeah, but you haven't given an exposition for x to the epsilon, so you don't need that iteration, right?
Well, yes.
You mentioned you can get an asymptotic formula for sum of lambda n equals 1. Like if you don't, like you said you can get, if you don't get cancellation in sum of in polynomial p, like can you prove sum of lambda n is the size of the interval with this method? If lambda n is n.
I'm not sure I get your question. So this works for general multiplicative functions. We have the same theorem. But we don't have a theorem which says that sometimes lambda n has many pluses, if that's what you mean. So, I was meaning that we have a general theorem in case that we have a multiplicative function which doesn't average to 0. It just says that it is the same as its average all along intervals. But we can't handle any sort of large values of puzzle sums or anything like that.
Maybe following up on that, is there, so I think we used here crucially that the function is bounded by 1, is that right, in magnitude?
We used that, yes.
So is there any way to remove that, or is that sort of a hopeless?
So we have different versions of the theorem which a complex version has appeared already, so you have to take care of pretentious things, but also we can do unbounded multiplicative functions as long as they are bounded on primes. We can do something on them as well, but it's not out yet.
Okay, see no further questions. Let's thank Kaisa again and then we can go off to tea.